Okay, so the diatomic gas, what we are going to do is that we are going to model it in the following way. We are going to say, okay, there is one atom, and there's another atom, and classically, they're basically connected by some sort of spring. Okay. So because of that, what we're going to say is that the moment of inertia along this axis, around this axis, is negligible. So we are going to say I3 is 0. But I1 and I2, which are the moment of inertia of rotation around these other two axes, they are non-zero, but they are equal. I1 is equal to I2 is equal to I, okay? So we're going to have three kinds of motion for diatomic gases. We're going to have translational translations. And then we are going to have rotations. And for translations, we are going to have 3 degrees of freedoms. For rotations, because we are taking one of these moment of inertia to be 0, we'll have 2 degrees of freedom. And lastly, we are going to have vibrations. And for vibrations, this is basically the oscillations in that direction. We are going to approximate the diatomic gas as a simple harmonic oscillator. And you can always do that because, whenever we have a system like this, that means that there is some sort of attractive potential between the two, right? So if I have an attractive potential, then it'll be something like this. We have some V, and then we have the distance between them, which is, say, R, and the potential energy is usually of this form. And if I look at the potential, around this region, the leading term would be a constant plus an x squared, r squared term, right? Some squared term. It'll be the leading term would be a. So for small oscillations, we can always, approximate it by vibrations, by a simple harmonic oscillator. So there's going to be only 1 degree of freedom associated with vibrations. However, both for the translation and for the rotation, there will be no potential. But for the vibration, there will be, the potential energy will not be 0. So, we can expect the equipartition theorem, as we derived it before, to be valid for these two cases, but because the potential is there, it won't be valid for this case, okay? And because these are...
Sir,
yeah?
I1 and I2 are the same, then don't we have 1 degree of freedom since we will know both of the
No, we don't.
moments?
I mean, they can still rotate into around those two axes.
Oh, I see.
Yeah. Okay, so because these are independent degrees of freedom, we can write the partition function for this particle to be the product of the translational partition function, the rotational partition function, and the vibrational partition function, okay? Okay, so translation would be as before, it'll be just the center of mass, degree of freedom. So translation will be as before, nothing to say there. And the rotation will be something new. And here you have to think a little bit. And so let me just draw a picture of to motivate the rotation. So this is the coordinate system. Hang on, this is not. Yeah. And suppose that this is our this is our molecule, the two atoms, and then if they're connected. Okay. Sorry, this is not a very good picture, but let me just try to see if I can improve. Okay, right. So, this thing makes an angle of theta with the y-axis, and it makes an angle phi with the x-axis. And if you think about it a little bit, and I will actually leave this as an exercise, but you can think about it a little bit. The kinetic energy associated with the two rotation will be half I omega 1 squared plus half I omega 2 squared. The first one, it's easy to see, is going to be I half I omega 1 will be just theta dot squared. And for the second one, it'll be half I sine squared of theta phi dot squared. And one way to see this is to actually say, okay, if I take theta to be 0, then of course the the contribution from this term would be 0, right? So these are the two kinetic energies associated with the axis of rotation of the two non-zero moment of inertia. So I wrote down the Lagrangian because it's easy to do that as a first step before we move on to the Hamiltonian, because the Hamiltonian should be expressed in terms of the canonical momentum. So what are the canonical momenta? So for theta, we get the canonically conjugate momentum would be given by this formula, and this is just nothing but I of theta dot. And the momenta canonically conjugate to phi should be given by this thing, and this is going to be I sine squared theta phi dot. Okay, so this just comes from the definition of the canonically conjugate momentum. And then I have a correction. In the last time I gave you the expression for the Hamiltonian, I gave it to you up to a sign, a minus sign. So the correct definition of the Hamiltonian is this. It has to do with the fact that we usually want the Hamiltonian to be a positive quantity. So this is the definition of the Hamiltonian. It is a Lagrange transformation of the Lagrangian, and you can see that this is the correct sign because the Lagrangian has a kinetic energy minus potential energy. So this minus sign flips the sign of the potential energy and makes it positive. So this is the correct sign. Okay, so the overall sign was wrong in a previous lecture. So now if I plug in the values of P and do a bit of algebra, just one line of algebra here, then we get the Hamiltonian, which is half P theta squared divided by I plus half P phi squared divided by I sine squared of theta. Okay, so this is the energy. So there are 2 degrees of freedom. So the partition function associated with the rotation, we should have 1/2 pi h bar squared, because we're dealing with only 2 degrees of freedom, so there will be 2 integrals. So there's d theta, d phi, which are the generalized coordinates, and dp theta, dp phi, which are the generalized momenta, then e to the power minus beta h rotation, where h rotation is the rotational Hamiltonian. Okay, so now what we have here are, first of all, we can do the p integrals. The p integrals are both Gaussian integrals because you've got p here, you've got p here, and once you do the p integral, what you have is you have 1 over 2 pi h bar squared 2I pi by beta, and then you have the theta integral, which is 0 to pi d of theta, and then sine of theta, and you have the phi integral, which is 0 to 2 pi, and that's just a trivial integral. And once you do all of this, you find the result, which is given by this. Okay, so the Hamiltonian for the partition function for the rotational degree of freedom is given by 2I by h bar squared kBt. And you can find out what the rotational energy is. The rotational energy is going to be minus derivative of log of z divided by the derivative with respect to beta, and they just gives you it just gives you kBt. So for translation, we got 3/2 kBt. For rotation, we get 3/2 of kBt. So if you look at the total energy, without vibration, so I'm calling it E prime. So E prime is not the real total, but it's 5/2 of kBt. And so if I now calculate what the heat capacity is for n particles, it's going to be 5/2 of kBn. Okay, so let's put a prime here so that we know that it excludes the vibration. Sorry, that's not how you spell exclude. Excludes vibration. So these are the. So now we have just the vibration left. Okay. So for vibration,
should the rotation be 3/2 since there are 2 degrees of freedom?
No, half plus half is 1.
I think it says 3/2.
Oh yeah, you're right. Yeah, thank you. Thank you. All right, so this is H vibration, and for that we can take the vibrational degree of freedom is, say, zeta. So we have 1/2 of m omega squared zeta squared. Zeta is the vibrational displacement. So this is the vibrational, and now if I just go through the same thing, and all you have to do is some a couple of Gaussian integrals. It's as simple as that. Then you can just work out what Z vibration is. So this is not something that needs to be done, and this just becomes kBt divided by h bar omega, where omega is the spring constant here, right? Or sometimes called K, but it's m omega squared is K. So if I look at the energy of the vibration, then what would be the, can anyone guess? Well, you can't guess.
Half of KT.
Sorry?
Half of KT.
Yeah,
Oh, sorry.
it would be half of kBT if there were no potential energy. But because of the presence of the potential energy, the equipartition theorem gets changed. And it's actually kBT, okay? So if I look at the total CV, then we have 5/2 of kBn from the translational and the rotational degrees of freedom, and then we have kBt. So the total is 7/2 kBn. Sorry, not T. It should be N here. This is the. So we can now go and okay. Before we go and talk about this result, the validity of this result, let me just make a few comments. One of the comments, it doesn't depend on, doesn't depend on I or omega. That means that if I is big, then it rotates more slowly, but such that the energy is still kBt. The rotational energy is still kBt. If it's very rigid, so that omega is big, then its amplitude is small, so that its vibrational energy is still kBt. So the energy does not depend on, or the sorry, not the heat capacity does not depend on either I or omega. The other comment is that this result is actually only valid at very high temperatures. So in the 19th century, when people actually did the experiment and compared it to this calculation, they found that this was actually not valid. So if you plot CV as a function of the log of the temperature, then you see that it does something like this. It goes like this, and then it increases, and it increases. And it's only, over here, the value is 7/2. Let this be CV by N. Over here, it's 7/2. And the value here is about 5,000 Kelvin. And over here, it's 5/2. And the value here is about 500 Kelvin, okay? And the value here is about 3/2, okay? And this is, 10 or 20 Kelvin. So it's only at very high temperature that, this result is valid. And the reason for this is quantum mechanics. The switching on of the degrees of freedom as a function of temperature has to do with the fact that we have not taken into account quantum effects. And one thing to notice is that over here it's about 2,000 Kelvin, that we associate quantum effects to be usually at small temperature, but even at a high temperature there can be quantum effects. And this failure, this discrepancy between the prediction and the result, prediction and the observation, was the first failure of classical mechanics, classical statistical mechanics. But this did not give birth to quantum mechanics. The thing that gave birth to quantum mechanics was the second big failure of classical statistical mechanics, which was the black body radiation. Okay, so this is a very important result. Okay, so I think I'm going to stop here, but are there questions? Okay, I will be assigning an assignment over the weekend, okay, the next assignment. And there will be another quiz next Thursday, and I'll tell you which chapters will be on sometime later today, okay?
Okay, sir.
Okay, sir.
Okay, well, thank you very much, and I will see you